Here we're going to use a simple example of a wire in a magnetic field to try and understand the basic concept of magnetic levitation. We know that if we have a wire in a magnetic field carrying a current, it will experience a force from that magnetic field. That magnetic force, FB, the magnitude of that force, is given by I times L times B times the sine of theta, where I is the current in the wire, L is the length of the current carrying wire that's in the magnetic field, B is the strength of the magnetic field, and theta is the angle between the orientation of the wire or the current and the magnetic field. Let's now shift our focus to the picture on the top right. I have a magnetic field which is directed to the right, and for the purposes of this picture, I want you to imagine us as looking top down. So the floor is like underneath this magnetic field, and the magnetic field is moving to the right, which would be parallel to the ground. Also parallel to the ground, but perpendicular to that magnetic field, we're staring top down at a piece of copper wire. So that copper wire is drawn there in yellow, and the length of the copper wire that's in the magnetic field is L. The strength of the magnetic field is 0.1 Tesla, and as I said, that wire is perpendicular to the magnetic field, but both the wire and the magnetic field are parallel to the ground. The first question that I want to ask is, in what direction should the current be traveling in order for the wire in this configuration to levitate, to be lifted off the ground? And remember, since we're staring top down on the wire, the gravitational force would be directed into the screen, and we need a force in order to lift up that wire that points toward us. So I'll leave you with that question for a moment. What direction would the current need to travel in order for the wire to be levitating? And now let's imagine this in a slightly different picture. I've drawn the same configuration but from a different point of view. Instead of staring top down at the wire, now we're going to kind of look at it edge on. So I want you to imagine yourself sort of standing on the ground here to the left of my picture, and if you were staring at that wire, then it would look something like the picture that I've drawn below. You would see the magnetic field moving away from you or into the screen, and you would be staring at the side of the wire. And so the ground in the bottom picture is actually kind of like below the wire and below where the magnetic field is. Still, we have the length of wire L. In this picture, it's a little bit easier to imagine which direction the forces are. So for example, we have a gravitational force on that wire that points downwards, which is equal to the weight of the wire, mg. And so the question I asked earlier was, what direction would the current need to travel in order to make the wire levitate? Well, here we can at least see what's happening with the forces. If there's a downward gravitational force, then there needs to be an upward magnetic force that points like that, and that magnetic force better be at least equal to the weight of the wire, so that way it'll lift it up. So we'll say that the minimum force that could be applied in order to levitate this wire would be a magnetic force that is equal to the weight of the wire, mg. If I wanted to add those forces to my top picture, what would they look like? The gravitational force, since this is a top-down view, would be going down into the picture, and so I could draw that gravitational force maybe something like, write mg, and then draw an x going down into the picture, and that means I need a magnetic force, FB, which is directed out of the picture. So I'll draw a circle and put a dot in it. So now looking at that top picture, in what direction would the current need to travel in order for the wire to experience a force from the magnetic field that's directed toward us, which would be away from the ground? And the way that we do that is with the right-hand rule. We point our fingers in the direction of the current, curl them in the direction of the magnetic field, and our thumb points in the direction of the magnetic force. And so with this orientation, you could either start by just pointing your thumb in the direction that you want a force. So for example, that magnetic force needs to be out of the screen, so you could orient your hand that way and work backwards. Or you could just try each direction of current and see which one works. If you take your fingers and point them in the direction of the current, let's say that is toward the bottom of the screen, and you curl your fingers in the direction of the magnetic field, which is to the right, so you're curling your fingers to the right, then your thumb will point out of the screen or toward you. And so the direction of current that we need is a current that runs from the top of the screen to the bottom of the screen. And so we could represent that in this way. In the bottom picture, what does that look like? I need my fingers to point to the right, which represents the current. My fingers need to curl toward the direction of the magnetic field, which is into the screen, and my thumb points upwards, right, which was the direction of the magnetic force that I drew in that bottom picture. And so in this picture, my current needs to be moving to the right. So that answers our first question: what direction does the current need to point in order for the wire to levitate? The second question is, what kind of current do I need to have in that wire in order to produce a force that is strong enough for this given strength of magnetic field? And for that, we need to know a little bit more about what's going on with the equation on the left. And the way we'll start is by recognizing that because the wire is perpendicular to the magnetic field, then theta in this equation will be 90 degrees. And so sine of theta is equal to 1. And so what I know right away is that the current times the length of the conductor in the field times the field strength is equal to the weight of the wire for the minimum force that we would need in order to lift up the wire. Now what I'd like to do is, instead of expressing this equation in terms of the mass of the wire, I would like to express it in terms of things that are more fundamental to the wire, like the density of the wire, which if it's a copper wire, then we would use the density of copper, and the volume of the wire, which for a certain length, L, which I already have in my picture, and a radius, which is determined by the thickness of the wire that you're using, then we can determine that as opposed to measuring the mass of the wire. And so what I'll do is I'll express this as ILB equals, and then the density times the volume of this wire is equal to the mass of the wire. So I've expressed it that way. And we should know that for a cylindrical object like this, the volume of that wire is going to be equal to pi r squared, which is the area, the cross-sectional area of the wire, times L, which is the length of that wire. So that whole term there represents the volume, times G. Now let's solve this for the current. I equals the density times the volume times G divided by length of the wire divided by the strength of the magnetic field. And the length of that wire is on the top and the bottom, so it cancels out, and what we're left with is rho pi r squared G divided by B. And so this expression for the current is a current that would be the minimum current we would need to levitate this wire. And the only things I need to know are the density of the material that makes up the wire, the radius of the wire, the acceleration due to gravity, and the strength of the magnetic field. I already gave the strength of the magnetic field up above, 0.1 Tesla, and now I'd like to give some reasonable values for the density and the radius of the wire, so that way we can see what kind of current we would need. So I'll add these values up above. The density of copper rho is approximately 8,920 kilograms per meter cubed. And let's say that the radius of the wire that we're using, R, is about 1 millimeter, or 0.001 meters. And so this is a pretty thin piece of copper wire. So let's see what the current would need to be. The current, I, would be the density, 8,920, times pi, times the radius squared, which would be 0.001 squared, times the acceleration due to gravity of 9.8, divided by the strength of the magnetic field, which is 0.1. And if you plug in those values, you'll find that the current would need to be about 2.75, and since I've used standard units for all those numbers, then that current will be measured in amps. 2.75 amps is a pretty substantial current. The last thing that I'd like to do is think about how this might practically work. So far I've just drawn a stray copper wire which is not connected to anything, so where would that current come from? Well, if we had some additional copper wires which were connected to the copper wire I drew initially, that might look something like this, then we're starting to get closer to a circuit. You could imagine maybe there's a power supply somewhere out here where the person is drawn that connects to those two wires that generates a current, and now we've got a closed loop where a current could flow. Let's also think about the orientation of those two additional copper wires that I've drawn. The power supply maybe is located in a place where the magnetic field isn't, but part of those wires that I've drawn, that I've added to that top picture now, are in the magnetic field. But if you notice, the orientation of the wires is in the same direction as the magnetic field. And so since the wire is pointed along the direction of the magnetic field, it won't feel a force. Just like if I have a charged particle moving in the same direction as a magnetic field, it doesn't feel a force from that magnetic field. So the only part of this circuit that feels a force from that magnetic field is the wire that I drew initially. So you might imagine this copper wire is very long, we have a strong magnetic field, a very high current, and we could use this thing to levitate an entire train.